Good morning, everyone. Welcome to our virtual Saturday Research Academy conference. This talk will be recorded. The agenda for today is here. So I'm welcoming you again to our Saturday virtual talks and conference. I'm Dr. Elba Sepulveda and will be the moderator for this activity today. Please remember to fill out the participant survey that will collect basic information about you, and this information will be used for reporting. You can be a student, a mentor, teacher, parents, or any general guest. You are welcome to fill out that. I will share the link over the chat. The reason that we are collecting this information is that our sponsor, the Citizen Diplomacy Action Fund, required us to fill out a report. And we also need from you that you fill the evaluation of this conference is a small survey. I know that sometimes we are collecting the email, but it is not for identify you. You can use a fake email and it will work. We don't want to have duplicated information, and sometimes people are submitting, twice. So that is the big reason. And please, thank you for filling all our surveys. And I will let Dr. Aratia talk to you now. Thank you so much for being here.
Okay. Good morning to everybody, and maybe good afternoon to others, to people from Russia. Today we had a very interesting conference. Dr. Tohru Yagi, he was a visiting scholar here in Puerto Rico. Basically where I met him, and his neural engineering is something very interesting for many of you. So without more talking about Dr. Tori, because we do have, you see, all the information at the web page, so you can go there and look for the credential of Dr. Tohru Yagi, and he's an outstanding researcher. So thank you very much, Dr. Tohru Yagi, for being with us. I understand it's late in Tokyo at this time, 10 o'clock p.m. So thank you very much for this opportunity. So the floor is yours.
Okay. Thank you very much, Dr. Aratia, and also the Elver. Hi, everyone. ¿Cómo estás, esta? My name is Tohru Yagi from Tokyo Institute of Technology, and I met Dr. Aratia in 2013, I believe,
yes,
when I was a Fulbright Scholar at MIT, and Dr. Aratia invited me to Puerto Rico, and I gave the lecture at the time. I still remember I had a great time in Puerto Rico, and someday, near future, I would like to visit again. All right, so let me share my slide. Okay. So everyone, do you see my slide?
Yes.
Everything okay?
Yes.
Okay.
Everything is good. Okay.
So let's start. Today, I'm going to talk about neural engineering. I think most of you major in engineering, but what is the neural engineering? Let me start with the explanation about neural engineering. This is a new interdisciplinary research area between engineering and medicine and neuroscience and cognitive science. So yes, the neuroengineering is something related to the biomedical engineering. And there's a neuroengineering conference and also the society. Under the IEEE Society, there is a neuroengineering section. And they define the neuroengineering as follows. Like imaging and mapping the brain, neural signal processing, modeling, neural nanotechnology, brain-computer interface, neuroprosthesis, neurorobotics, blah, blah, blah. So today, I focus on the brain-computer interface and neuroprosthesis since my research area is related to these two topics. So I focus on the brain-computer interface and neuroprosthesis, and you will learn many things in this field. So in general term, it's called neural interface. The neural interface is general term, including brain-machine interface and neuroprosthesis. And this neural interface includes stimulation interface and recording interface. In case of the stimulation interface, machine give the signal to the human body. And then we can obtain some information from outside, like a visual information or auditory information. And in case of the recording, we can record a brain activity or nervous signal from our body and then let the machine work. For example, controlling the prosthetic arm or maybe the controlling a wheelchair. So the neural interface is the very new technology. Well, I can say it has a very long history, but recently many people pay attention, a lot of attention to this neural interface. So this neural interface can be categorized into 4 different types. The stimulation type and recording type, that's what I mentioned already. And they are categorized into the invasive type and non-invasive type. So in case of the invasive type, the system or the device will be implanted inside of our body. So invasive stimulation type, those are called neuroprosthesis. And invasive recording type is called brain-machine interface. On the contrary, in case of the non-invasive type, non-invasive stimulation type, there's a surface electrode, functional electrical stimulation, FES. And non-invasive recording, they're called brain-computer interface. In this lecture, I would like to talk one by one. And first, let me start invasive and stimulation neural interface. Well, when I talk about the stimulation, maybe I should start with this story. Galvani's experiment long time ago, 1700. He applied 2 different types of the metal to the frog leg. And then he found out the frog leg was moved. It was astonishing facts at the time. And this is the this is a starting point of the stimulation to our biological system, especially the muscle. And this finding now applied to the certain type of neural interface. Oh, but before that, let me show you this simple biological experiment. I think some of you have did the similar experiment. That this is the electrical stimulation to the frog muscle system, frog muscle and also frog nervous system. It's called a sciatic nerve. And then stimulate, and you see the frog's leg is moving, or the body is moving. So just like a frog, our body also reacts to the electrical stimulation. And using this scientific finding nowadays, we implant this type of cable or electrode into our limbs, for example, the arm. In this patient, he received the electrode implantation around his arm muscles. You see this X-ray photo, and these wires, they are electrodes. And sequentially, the electrical stimulation would apply to those muscles, so that this a spinal cord injury patient can hold glass and lift it up, and yeah, he can use his arm. So this is because of the electrical stimulation to the muscles. He can control his paralyzed arm and fingers. And this system is called functional electrical stimulation, FES. Well, next, I'm talking about the stimulation to the brain or nervous system. When I talk about the brain stimulation, well, I should mention about Dr. Jose Delgado. He was a professor at Yale University in 1950s, and he did a remarkable experiment. He invented a very small stimulation device. Now he's holding something on his hand. This is the device. It's called a stemoceiver. And he implanted this stimulation device into the animal's brain and also the human brain, and he did a lot of pioneering work. The most famous experiment was he implanted this device into the bull. And bullfighting in Spain, that is very famous. And Jose Delgado, Professor Delgado, yes, he was from Spain, and yeah, that's why he implanted the system to the bull. And
in the
let's
1960s,
take a look at this
Professor
video.
Jose Delgado took a normally hostile bull and implanted electrodes into its brain, electrodes that could be activated by a radio transmitter. His objective was to see if stimulation of the bull's midbrain could short-circuit the rage signals, stopping the bull before it reached the matador. After the bull had recovered from the implantation and in mid-charge, the button was pressed. The bull's aggression ceased instantly, or so it seemed.
So, well, actually, this is Professor Jose Delgado. Now, he holding the red mant, and then the bull start running to this red cape, but because he holding the remote controller and he switched on, and he could stop the bull's movement. So this is the first experiment in 1960s, and after the 20 years after his experiment, nowadays we have this type of device. It's called deep brain stimulation, DBS. The DBS is the stimulation to the deep part of the brain, and then this is a treatment method for Parkinson's disease. Do you know the Parkinson's disease? Well, later I will shortly I will explain Parkinson's disease. Well, this DBS is also called brain pacemaker. Just like a heart pacemaker, there's a controller, and then the cable is here, and the electrode is inserted inside of the brain. And this is X-ray photo. Now, the pair of the electrodes are implanted almost the center of the brain. It's called substantia nigra. That is the name of the place. But this very deep part is stimulated electrically, and then the Parkinson's disease will be controlled. I mean, the symptom of the Parkinson's disease is controlled. The next video shows that typical symptom of the Parkinson's
2年ほど
disease.
前から一日中ベッドで過ごすように
So
な
the
りました。
Parkinson's disease patient,
起きれるんだね。
their
ね。
the leg
それでや
or
っぱり
hands
そういう
has a
な
very
んか
severe
ちょっと止
tremor,
めてないともう
shaking
倒れちゃう
all
から
the
ね。
time.
うん
And it's very hard to move around.
西郡さんは夫に支えられ
In
て
her
ようや
case,
く歩
yes,
くことが
she
できま
need
す。
help from her husband to walk. This is the typical symptom
体が
of Parkinson's.
痛いの。
But if you implant the electrode of the brain and stimulate, this symptom is dramatically improved. The next video shows you will see the improvements of the Parkinson's disease. Let's see. This person
しかし
looks
11年前に体の震えが
but
止ま
he
ら
is
ず動けなくなり難
Parkinson's
病
disease
パーキン
sufferer.
ソン病を発
Now
病したと
he
いうので
has
す。
the DBS in his head. This is a controller.
リトルさんの脳には今も電気信号が24時間送られています。その効果を見せたいとリトルさん
And
は
he's
自
gonna
ら
turn off
リモコンで電源を切りま
his
した。
system in order to
And I wait until I
show
hear it beep, beep. Did you hear that? And then
the
that side
effect
is
of
off.
the DBS.
And I will do the right side.
Now he turned off the DBS. Let's see what's happened.
5分後
5 minutes.
異変が現れました。
I feel my face drooping.
It's changing.
You see that?
Oh, yes.
I mean, I know that
And he started shaking.
この治療法は病気を完治させるものではあり
have
ません。
Parkinson's
Now this is
who may
typical
watch this
電源を切れば
program
元の体に戻ってしまうの
what
で
it's
す。
like. And to see me as good as I have been without seeing this part of it would find it hard to believe. So I wanted to get, speech pattern, speech, keep up with my brain. I know what I wanna say, but I
Could you turn it on? I think it's.
Turn yourself on. Top blue one.
the top button on the right.
Now it stopped.
Yourself again.
I think so.
How do you feel?
Oh, is my whole face smiling again?
Yes.
Okay, what? Go back through there again. What is that?
Oh.
Oh,
Amazing.
it's a miracle, is it not?
Is it?
It's
Technology
amazing.
is wonderful.
It's amazing how it happens, and I don't know how he did it, but he did it.
Technology is
So
awesome.
this is the DBS. Let me explain the next topic. That is a cochlear implant. A cochlear implant is a stimulation to the auditory nervous system. The device has two components. One is external device and internal device. And external device receives auditory the sound information, process it, and then transfer the data to the internal device. And the internal device receive the data and generate the electrical stimulation pulse, and then the pulse will be applied to the auditory nervous system. Well, surprisingly, the first person who did the electrical stimulation to the auditory system was Volter. Of course, you know the Volter. He is he's a pioneer person of the battery. Yes, and after he invented his first battery, he did one interesting experiment. He connected the cables and then insert the cable into his ear and stimulate it electrically. I don't know why he did it, but he did it. And he, at the time, he heard some boiling sound, like boiling the soup. And this is the first time for the human being to hear the sound with electrical stimulation. And then the people start working to make the cochlear implant. 1950s, and nowadays we do have this type of the cochlear implant. That's a small device. This is the implant, and you see the cables here. And this cable will be implanted inside of the cochlea. Cochlea is a very small hearing organ in our ear. And then this is the external device. And external device is hang in your earlobe, and this is the antenna. Okay, this schematic diagram shows how the implant will be inserted into our ear. And here, external device and internal device. And the internal device receive the data and then send the signal, electrical stimulation, to the cochlea. The following video explains the mechanism. Let's take a look at.
Millions of people suffer from hearing loss. For those who no longer benefit from hearing aids, cochlear implants may be the next best step. For most people, severe to profound hearing loss results from damage to fine sensory hair cells in the inner ear. A cochlear implant bypasses the damaged hair cells and sends electrical signals directly to the hearing nerve and onto the brain. It all begins with the microphones, which capture sound waves approaching the ear. Then, the processor, shown here worn over the ear, converts the sound into digital signals. These signals are sent to the headpiece, which in turn transmits them to the connected implant and onto the inner ear. The hearing nerve receives signals from the implant and sends impulses to the brain, which are interpreted as sound. For people who don't benefit from hearing aids, CI technology makes it possible to perceive sound. The result? A revolutionary restoration of hearing, connecting you or your loved ones to the world of sound. An experience not possible with hearing aids alone. At Advanced Bionics, we're here to help provide a solution.
Okay, so as you see, the cochlear implant, this gives a dramatic, astonishing results. People can hear the sound again. And of course, if we increase the number of the electrodes, the sound quality gets better. But there's some simulation. If people use only one electrode, and what do we hear? Let's see. Do you understand? One electrode stimulation. It's really hard to understand. Oops, sorry. Oh, once again, let's hear. Actually, it says.
The boy did a
but
handstand.
if we increase the number of electrodes up to 4, maybe you can hear something once again. Actually says.
The dog growled at the
and
neighbors.
If we use 12 electrodes.
Time, good, pray, fight, pie, cut.
And this is.
Time, good, gray, fight, pie, cut.
So from this simulation, computer simulation, you understand the number of the electrodes is closely related to the quality of the sound. So if we increase the number of the electrodes, like up to 100 or 1,000, maybe we can create a better sound. Is it? Actually, no. Well, yes, the cochlear implant researchers, they did the experiment. They implanted 60 electrodes so far. But there's some crosstalk between the electrodes, and the restored sound quality was not so good. So nowadays, people use around 20 electrodes. Yeah, probably the 20 would be the optimum for at this moment. but in the future it might be improved. That this is a cochlear implant. Next, okay, because the cochlear implant is the most successful neural interface, some vision people started to research the visual prosthesis. I am the one to study the visual prosthesis, but the visual prosthesis, just like a cochlear implant, consists two type of units: external device and an internal device. The external device has a camera, processor, and data transfer unit, and an internal device, data receiver, and then pulse generator and electrode array. This array will be implanted into retina or optic nerve or the visual cortex in our brain. So there are several research groups to study the visual prosthesis. Some of let me show you their outcomes. For example, the Dover Institute. They implant the electrode in the brain and stimulate the visual cortex, and they successfully restore the visual sensation so that this person can drive a car, and if there's some obstacle in front, he can, yes, use a steering wheel and he can turn. And this group, German group, they implant the electrode inside of the eye and stimulate the retina.
There's a knife here, and this one looks different on the right, so I would say it's a spoon, and then there's a mug here.
And some products has been already commercialized. The US group, the second site in Los Angeles, yes, they commercialized the product to year 2012, and now it's available on the market. How many electrodes will be required for restoring the visual sensation? This is a simulation, and if we implant more than 1,000 electrodes, yes, people can see the shape. But at this moment, the number is very limited. The number of the electrodes is less than 100. So our next technical challenge is how to increase the number of the electrodes which will be implanted inside of our body. Okay, next topic. Let's go to stimulation and non-invasive type neural interface. First, let me show you the bionic glove. The bionic glove, this is the device for someone who has a paralyzed arm. Let's take a look at the video. In this device, stimulation will be applied to the arm muscles from the surface of the skin and the left without stimulation. And this person has a very hard time to hold the object and lift it up. But the right hand side, this is the electrical stimulation. He can easily control his arm movement. This is a research done by University of Alberta, Canada. But nowadays, this is already commercialized by the US company. It's called Nest. The system is called Nest. Okay, let's take a look at their video, promotional video.
Changing the way we treat paralyzed hands. The NES H200, a breakthrough development in physical medicine and rehabilitation. This advanced neuroprosthesis and rehabilitation system is designed to improve hand function, while reducing complications associated with disorders and injuries of the central nervous system. The NES H200 consists of an electronic orthosis and its control unit. The control unit transmits synchronized electrical pulses to the peripheral nerves through electrodes built into the orthosis. These pulses accurately and consistently activate 5 muscle groups of the forearm and hand: the extensor digitorum, extensor pollicis brevis, flexor digitorum superficialis, flexor pollicis longus, and the thenar group. Based on clinical evidence and tested by thousands of patients, the NES H200 was designed to provide proprioceptive input and synchronized functional muscle activity. These movements may facilitate normal patterns, leading to the reversal of learned non-use.
Okay, let me stop. And this company also invented the leg type prosthesis. And if you are interested in the product, maybe you can Google NES. Okay. The next neural interface, that is non-invasive and recording. That is called brain-computer interface. The first one, that is an EOG controlled device, which our research group invented. Now, you see the electrode around his eye. And this electrode picks up the patient's eye movement. So this patient can make the buzzer beep sound, make the beep sound with system. So it's called EOG. EOG is a signal from around the eye. And also, maybe you know the muscle signal. The muscle signal is called EMG. And using this EMG, now it is possible to control the robotic arm. This video is a simple experiment of the robotic arm control using EMG, 1990s. And based on such basic research, nowadays,
pattern recognition controls terminal devices with artificial intelligence.
EMG-based
The
prosthetic arm
MyoPlus prosthesis control uses up to 8 electrodes to measure incoming signals of the forearm and derives patterns that are characteristic for individual movements. Complex mathematical algorithms transform and amplify these signals and patterns so that a prosthetic hand can translate them into the corresponding movement.
And using this is, people already use this in daily life.
The biggest difference is that you don't have to relearn everything. Now I just do open hand with the phantom hand, and the hand opens. And when I do close hand, it closes. The hand actually feels the same as the sound hand in your mind. The thing that I always found difficult with the other control system was that you had to switch. The big advantage of the MyoPlus app is that you can easily change a wide range of settings yourself. The fact that you're not thinking about how to grasp something anymore means that you essentially grasp it the same way you would with the sound hand. So I use it much more often. The Greifer, the Very Plus Speed, and the B Bionic Hand are all compatible, and exchanging them is simple and extremely quick. With the new MyoPlus control system, you simply open the hand, think about the grip that you want to use, and the hand goes ahead and executes the grip.
Okay, now let me stop. So yes, such a system is already commercialized, and one company is called Autobug. This is a major manufacturer of the EMG-based prosthetic arm, and you can find similar system if you use Google. And if you're interested in, maybe you can Google and find similar products. Okay, now next, the controlling the system using brainwave. It's called BCI system, and apply the electrode on the surface of the head, and then record the neural activity. And we can record the brainwave. It's called EEG. Now, using this EEG, we can control.
Researchers in
the,
Japan have developed a brain-machine interface that allows for control of a wheelchair using
wheelchair.
thoughts alone.
For example,
In this video, released by government-affiliated research unit RIKEN, the thought patterns of the researcher are being picked up by electroencephalography, or EEG sensors mounted on his head. The data is relayed to a laptop computer that interprets it and turns it into control signals for the wheelchair. The system was developed by RIKEN and Toyota Motor, Toyota Central R&D Labs, and Genesis Research Institute. With as little as 3 hours training per...
So as you see this video, many research groups, including Toyota Motor Corporation, yes, they developed such a brain control system already. Lastly, let me explain the brain-machine interface. That's the invasive and recording type. In this type of the neural interface, they use the neural activity from the motor cortex or the sensory motor cortex, sensory cortex. And some researcher, well, first of all, they studied the animal. Some researcher recording the neural activity from the motor cortex during the certain animal experiment. And they find out it is possible that in their experiment, this is a very simple experiment. Let the animal press the lever so that this animal can drink water. And they record the neural activity. But eventually, they change this system. And then this rat start drinking without hand movement. And they wonder why. Because this rat can generate certain brainwave without a hand movement. Well, I think the next
その結果できたシステムです。レバーを押すと蛇口が出てきて、ネズミは水を飲むことができます。次第にネズミは学習し、水を飲みたいときは前足でレバーを押すようになりました。この時、ネズミの脳に電極を差し込みます。水を飲もうとしてレバーを押した時に出る脳の信号を記録します。
They record the neural activity from the motor cortex. This is the first step. Pressing lever, and then they could record the neural activity from motor cortex.
レバーを押すと蛇口が出る回路。この後、この接続を切りました。
They cut off the line.
蛇口をレバーの信号ではなく脳からの信号で動く回路に切り替えました。ネズミは前足でレバーを押します。その時脳から出る信号だけでコンピューターが作動し、蛇口が動いて水が飲める仕組みにしたのです。シェーピン教授が考えた通り、脳から取り出した信号だけでネズミは水を飲むことができたのです。
Still, there is a lever movement, lever pushing movement.
この後、予想もしないことが起きました。ネズミが前足を動かさずに水を飲み始めていたのです。
The rat didn't move the lever, but still it's drinking. It means
ネズミの脳は前足を動かさなくても動かしたのと同じ信号をコンピューターに送れるようになっていたのです。
So it means this rat just think the hand movement and then this brainwave control this system. This is a great finding, and eventually this finding was applied to the human being. And if you are interested in their research work, maybe you can check the Nature and their paper. And the system is called the brain gate.
It says you are
Let's
doing a
take a look
great
at this
job.
video.
Next, I'm going to open the second email, which states, "Hi there." It says, "Hi, we'll talk soon." Now I'm going to the exit. Next, I'm going to paint a circle.
You see the device on his head. The electrodes implanted inside of the skull. And this is a head amp.
That's the best circle I can do. Now I'm going to exit.
And based on the brain activity,
next I'm going to turn on my television. I'm going to
he
hit the power
can
button to
control
turn
the mouse
television on.
cursor.
The television is on. I'm going to channel down. There's channel down. Now I'm going to channel up. There's channel up.
And you see the connector here.
I'm going to paint a circle.
So this system is wired system. There's a connector, and then the cable is coming out, and then it is connected to the computer.
To exit.
Not only the computer cursor, in using this system, that he can control the prosthetic arm.
Now close.
All he needs to do is just think. Think of the hand movement.
Not there at all.
So that he can control the mouse cursor and also the prosthetic arm. And this system nowadays is improved by a certain person, Elon Musk. You know, of course, you probably know that Elon Musk established one startup company. It's called Neuralink, and Neuralink developed a wireless system, just like this. And recently, they implant this system into the monkey and did some
we calibrate
experiments.
the decoder by recording neural activity as Pager uses the joystick to move a cursor to targets presented on the screen. As he's playing this game, we're wirelessly streaming, in real time, the firing rates from thousands of neurons to a computer. Using these data, we calibrate the decoder by mathematically modeling the relationship between patterns of neural activity and the different joystick movements they produce. After only a few minutes of calibration, we can use the output from the decoder to move the cursor instead of the joystick. Pager still moves the joystick out of habit, but as you can see, it's unplugged. He's controlling the cursor entirely with decoded neural activity. Our goal is to enable a person with paralysis to use a computer or phone with their brain activity alone. Because they wouldn't be able to move a joystick, they would calibrate the decoder by imagining hand movements to targets. One of the things the Neuralinks allow Pager to do is to play his favorite video game, Pong. To control his paddle, on the right side of the screen, Pager simply thinks about moving his hand up or down.
Without any hand
We've
movement.
removed the joystick altogether. Now that he's up to speed, let's increase the difficulty and see how well Pager can play with the Neuralink.
So, well, that's all for today. Maybe you can understand what the neural interface is. Now technology is now at this level, but soon those technology will be improved, and then will help the people, especially the disability people. If you are interested in this technology, maybe you can take a look at these websites, IEEE MBS Neuroengineering, or Society for Neuroscience, or NIH also has some program. So those are information sources. Okay, thank you very much. Oh, sorry to extend time. If you have any question, I'm very happy to answer. Dr. Ratia, and also the Dr. Elber.
Yes, thank you so much for all the information that you provided. And I am very impressed about all the technology that we have right now, especially the one that you show at the end. And I know that we have a lot of participants that they do have some questions like, I don't know, when do you think that will be available for people or something like that?
I can say soon. Well, at this moment, there's an animal experiment, but after the animal experiment, and they're gonna start the human trial soon, and if they confirm, once they confirm the safety issue, and then the product will be applied to will be commercialized at the clinical stage.
Thank you.
It doesn't take long.
Let's open the floor for questions. Do you have questions? You can put your questions on the chat if you want to, or use the microphone to ask questions. Hi, Kevin. Do you want to make a question?
Or you can leave the message on chat.
Yes,
Okay,
we have a question on the chat. It is, are there neural prostheses for animals?
For animals. Some, as I explained, some of them are animals, but some of them already commercialized and applied to the human being. Well, neuroprosthesis has a long history, as I explained, and more than 50 years. And cochlear implant, I think 37-year history. DBS, this is also more than almost 30 years. And what else? Yeah, the many products has been already commercialized and applied to the patients. But the last one, brain-machine interface. Still, it's under the animal experiment, but probably within 10 years, I think that product will be applied to the humans, available on the market.
We have another question from Gabriela Molina. It is, I have a question for a myoelectric control properties device. Which are better, electrode implants or surface electrodes?
Okay. Well, if you talk about signal noise ratio, SNR, implant device has the better SNR. But availability, surface electrode is much easier to install. So I think it depends on the user's needs. And if they want the device without any surgery, they're gonna choose a surface electrode type. And if they wanna have something more sophisticated or elaborated one, they're gonna choose the implanted device. There's one myo EMG controlled prosthetic arm. In that product requires surgery. They implant the electrode inside of the arm, and then they can control the prosthetic arm. So you can choose either one.
Do we have more questions? Thank you so much for your answers, Dr. Tohru Yagi. I think that all the information that you are providing to us is very impressive. Do we have questions? I know that Dr. Aratia wants to talk. You need to unmute yourself.
Yes, Dr. Tohru, with respect to the Neuralink, you see, when it's going to be available? Just because there is the company is going in the research cycle is already, but in the commercial one, do you think it's going to, the product is going to be available during this year or when?
Well, as I said, the Neuralink, I think they have done the animal experiment already, and probably they have already started a clinical trial somewhere.
Yeah.
But normally it takes about 10 years.
10 years.
To obtain that. Yes, the clinical trial normally takes 10 years. For example, in case of the visual prosthesis, people started the visual prosthesis research in mid-90s.
Yeah.
And then the one company, Second Sight, they commercialized the product year 2012.
Yeah.
So it takes about 10, no, more than 10 years, 15 years at the time.
Right.
But probably the Neuralink also, probably it takes 10 or 15 years to commercialize the product.
Some people think that it is it's not that expensive to to research or to have those, but I am feeling like 10 years of research is a lot of money that they needed to invest to be able to to construct something. Do you have an idea of how much?
How much?
Well,
for example, in case of the cochlear implant, the cochlear implant costs about few about let me convert.
No, you're okay. You're okay. More than
$20,000 US dollars, the cochlear implant. And the visual prosthesis, it's now I think it's a 50,000 US dollars. And probably the Neuralink system is, yeah, something around that range, I think.
Okay.
So it seems that that is maybe the cost for the user of that or to the person for buying that. But well, I realized that, that sometimes when you are running that kind of research, you will need to have a lot of money to invest for making the research, and then you can have that available to the users. And people sometimes they don't know that it is a lot of money that they needed to invest, like millions. So
but government,
I'm okay.
For example, in case of the US, the government spend a large amount of money to neuroprosthetic research. For example, DARPA is a part of the Pentagon, and they spend a large amount of money for the brain-machine interface research.
Yep.
Thanks.
And also the National Institute of Health, the NIH, also spend a lot of money.
Yes. All right. I think if there is no more question, I thank you very much, Dr. Tohru Yagi, for this great
my pleasure.
Conversation. Yeah, and the student really, they can really go back to the presentation and the links for the more information if they are interested to go forward in this area. Okay. So
yeah, there are lots of information. So you can search the information by yourself and find more information from the web.
Perfect. Excellent. So thank you very much, Dr. Tohru Yagi, for this opportunity. And
well, thank you very much for giving me such a great opportunity.
Yes. Yeah, we had over 30 30 participants. So we have participants from Moscow, participants from Dominican Republic, from Puerto Rico, from Chile, and from Nicaragua. So it's a broad spectrum of participants. So we really appreciate it.
Okay, thank you very much for audience. Yeah, audience, thank you very much for hearing my presentation. So hope to see you.
Thank you. Yeah, of course,
Thank you
yes.
so much. And before you go, yes, thank you. And before you go, remember to fill the participant survey and the conference feedback. Our sponsors, that are Citizen Diplomacy Action Fund, was created, because of the Fulbright Award. Also, the Scientific Caribbean Foundation is also one of our sponsors. So please visit our website to have more information about the conference that we are giving all the Saturdays. I put all these links, well, the first two, on the chat. So you will be able, to go in and get the information. Our next presentation is going to be next Saturday. It is Maria Dainori. So she's going to talk about gamma rays burst. You are invited to come. And remember, if you see here the scientific foundation in Puerto Rico website, you can have the links to register. So thank you to all for being here. I will show you also the attendance verification form. Remember that when you screenshot this one, please take a screenshot of the date of today and the hour, so you will have, the certificate with the right time stamp. Thank you so much for being here.
Oh, something else for the audience. You see, this tape, this talk is being taped, so it will be available in the webpage of the Dr. Tohru Yagi site. Okay, great. You want to just go forward again. Thank you very much. See you then. Have a good day, everybody.
Yeah, thank you very much. See you sometime. Near future, hopefully.
Yes. Yes, in the near future, not in the far future, in the near future. Great.
Yeah, yeah.
Excellent.
Okay, stay away from coronavirus, everyone, and stay healthy.
We will take care. Everybody has to take care. Right.
Yeah.
Excellent.
Okay, bye-bye.
I will stop recording. See you soon. Okay, bye.
Bye-bye.
Bye.